Okay, I have a problem. We have a spacecraft on the far side of the moon, receiving orders and sending us really cool pictures of the far side, like this one here. But, like, how is it sending us pictures when there's a big, hunk of rock in between us and them? So we know the moon has a near side and a far side, right? Because over millions of years, the tidal forces on the moon have slowed its spin down so that it's spinning at the same rate it orbits the Earth. What this means is that we only ever see one side of the moon, wherever it is in the sky. Whether it's waxing or waning, whether we're in Australia or the UK, we're familiar with that one face because that's all we see. And what's funny is because of the conservation of angular momentum, while we've slowed down the moon so it's tidally locked with us, the moon's actually slowed down our day as well. 4 billion years ago, we actually had a day that was 6 hours long, and that slowed right down to 24 hours. This is happening at such a slow rate that before we ever spin right down to only be facing the moon on one side, we will be swallowed up by the inevitable heat death of the sun as it expands into a red giant. So you've not got anything to worry about. Right, so we know that because of this thing called tidal locking, there's a near side and a far side of the moon, commonly called the dark side of the moon, though it does actually get days and nights as well, so thanks Pink Floyd. But right now there's a rover on that far side of the moon, taking measurements of the rocks and the composition of the rocks out there, taking pictures and sending them back to us, and even taking readings of the radio waves coming from space. It's seen as a great place to take these readings because you're not getting any signals or interference from Earth. But that's just my question. If they're not getting any signals or interference from Earth, then how are they communicating back to us? Now the answer is pretty interesting. So before launching the spacecraft with the moon rover on it, the Chinese Space Agency actually launched a satellite to sit in a stable orbital position on the far side of the moon. This sort of stable orbital position is actually described by maths that's like over 200 years old, by a guy named Lagrange. He was French, let's call it Lagrange. So when you have two bodies that are orbiting around each other, especially one that's very big and one that's quite small, you have these points in the orbit called Lagrange Points. So for every system with two bodies, you've got 5 Lagrange points, labelled L1 through to 5. And some are pretty easy to explain and some take a little bit more thought to work out why they're there. Because of these points, we can actually hold man-made satellites in specific locations in space without using too much fuel to keep them there. It's also in these Lagrange points that you tend to have clusters of asteroids or space stuff just hanging about because the gravity just kind of pulled them into that one place. So let's start at the beginning. What is L1 and why is it a Lagrange point? So if we look at L1 on its own, what we see is there's a force pulling it towards the Earth and another force pulling it towards the moon. So you can see quite quickly that at this point the forces cancel out and L1 is held at this point between the Earth and the moon. Another way to think about it is that if there was something orbiting the Earth at this point, it would actually orbit faster than the moon is because it's closer to the Earth. But because of the pull of the moon, it orbits slower and so therefore orbits at the same rate the moon does. We've actually already taken advantage of the L1 point between the Earth and the Sun. At this point, you always get a clear view of the Sun without the Earth getting in the way. We have our Solar Heliocentric Observatory and our Deep Space Climate Observatory sitting in that L1 Lagrange point already. L2 Lagrange point that we use to actually keep a satellite on the far side of the moon. So I'll explain that one at the end. L3 is on the opposite side of the Earth from the moon, and it sits just a little bit outside the moon's orbit. So if you think about this one, this would normally be orbiting the Earth slower than the moon is because it's sitting a wee bit further out from the Earth. But because of the extra gravity from the moon itself, it stays in that position opposite the moon. We've not found much use for the L3 point yet. That's because the moon isn't that big, the Earth's not that big, and so it quite often gets knocked out of that orbit. And because L's 1 to 3 aren't stable Lagrange points, you require energy to keep it there whenever it gets knocked out. L4 and L5 are stable Lagrange points though. And what that means is that any object near that point will tend to drift towards that point or oscillate around it. These points happen when the Earth, the moon, and the point in question make an equilateral triangle. That means the distance between the Earth and the moon, the Earth and the point and the moon are all the same length. So at these points, you don't need to calculate the distance to work out the gravity, since the distances are the same. And the gravity pulls the satellite towards the centre of mass of the Earth and the Moon. So that means as the Earth and the Moon spin round in their orbit, the satellite gets pulled or pushed at the same rate that they do, staying in that stable orbit. So if the satellite was to get knocked out of that point, it would actually get pulled back by gravity and hover around that point. It's the L4s and L5s across our solar system where we find the most natural satellites, that's asteroids and moons. In fact, an asteroid that's found in L4 and L5 are called Trojans. Earth has one known Trojan, lovingly called 2010 TK7. And then there are plenty of other asteroids and moons and other planets' Lagrange points. And then the last fun fact about L4s and L5s is that since the 70s, there have been discussions of having a space colony in one of the Earth-Sun L4s or L5s. The advantages being it would stay the same distance away from Earth the whole time. Although I've already talked about growing plants and having colonies in space, which you can see by clicking the card. So lastly, we have the L2 point, which sits beyond the Moon. So again, if we think about this point further away from the Earth, it would normally orbit slower around the Earth than the Moon would. But because of the extra gravity given to it from the Moon, it orbits faster and stays on that straight line that goes through the Earth and the Moon. Like L1 and L3, this is an unstable Lagrange point, meaning that if it gets knocked away, it will tend to drift away from that point, which means that the satellite on the far side of the Moon does need station keeping to keep it in that point. So using this satellite, which is orbiting Earth on the far side of the Moon, our little Moon Rover can send pictures and messages to that satellite, which then relays that back to us on Earth. The other L2 point that we use is the Earth-Sun L2 point, which sits even further away from the Sun than the Earth does. We use a satellite in the Earth-Sun L2 point to detect background microwave radiation from the Big Bang. That's because this satellite is permanently further away from the Sun than the Earth is, and so it can look out into deep space. So there we go, I've taken you on a journey through our solar system where scientists are placing satellites in Earth in certain places using maths that is 200 years old. And my question for you is, have you ever seen a satellite from Earth? You can use an app to see them, and they're often best seen either at sunrise or sunset, where the sun still lights up things that are higher up in the sky. Anyway, let me know in the comment section if you've seen them and we can nerd out together. I hope you enjoyed this episode of Science with Steph. If you did, be sure to give it a like and subscribe so you don't miss any more videos. In the meantime, if you want to watch more videos on space, you can click this playlist here. Or if you want to watch the videos that the YouTube algorithm thinks you'll enjoy best, you can click here. Anyway, I'll see you next week. Bye! The Spidey's chasing pigeons. Oh, excuse me.